everything you see here is a group that in some sense we've done before. Cyclic groups, the symmetric groups of permutations, the alternating group, which is the even subgroup of those permutations, D, and the dihedral groups, the Klein 4 group, V. Those are all finite groups. Then we've got the integers, the real numbers, the complex numbers, the rational numbers. There are many other sets of numerical ideas we can use. I gave you a basis for a starting group for such a thing in the exam called H. The complex unit circle under multiplication. The interval, the real numbers from 0 to C, including 0, excluding C, mod C, under addition. An infinite permutation idea. Remember, we talked about x cubed and showed that x cubed, the function, was a permutation. It was one-to-one, it was onto, from the reals to itself. That's a permutation, but it's not something we spend a lot of time on. And then the matrices, GL and R. Again, we have finite groups, we have infinite groups. These are my building blocks. And that's a scary statement in and of itself. I want to use these to build other groups. Now, to make my life easy, I'll start with the cyclic groups, Zn, as my building blocks. But if I can do it for those, I can do it for the rest of them. And you've seen this, even though I didn't tell you that was what we were doing. What I need to do is I need to reach back to discrete again and remind you about a set theory idea. The Cartesian product. The Cartesian product of a given pile of sets is a set of ordered however manys, ordered pairs, triples, quadruples, quintuples, n tuples. S1 through Sn are my groups. A1 through An are elements where each of those Ai is an element of the set Si. Usually, we write this as a product. S1 cross all the way through to Sn. Sometimes we write it as a product with a capital Pi for our product notation. I could do infinite sets. We'll save that for another course. I'm not going to do it here. This is why we write the plane as r squared and three-dimensional space as r to the third, because it is r times r times r, an ordered triple where each element is a real number. This is the general idea for Euclidean n-dimensional space, linear algebra people. Don't make this up. I want to do that. I want to do that where each set is a group. All right, wait a second. If I'm going to do this with groups, I need a group operation. Because what I've created is now a set of ordered group elements. What's my operation on those things? Now, I know that each individual group already has an operation, right? There's some operation *1 in group 1. There's some other operation in group 2. There's another operation all the way up to group n, right? Each of them has their own individual operation. So what if I said, when I take an ordered n tuple and I multiply, I'm going to use my multiplicative notation because I don't know what this group is, by another element, I'm just going to do this by component. So do A1 with B1 with whatever operation was in group 1, because A1 and B1 are both in group 1. Similarly, A2 and B2 are both in group 2. So I'll use whatever operation is in group 2 all the way up to AN, BN. And I'll do this component-wise operation. Now, I said earlier, you've seen this before. Take out exam 1. I'm a sneaky bastard. I'm a sneaky bastard. We have a set of ordered pairs, A, B, where A is in the element is in the group Z4 and B is in the group Z7. And I want you to do the operation of component-wise addition. When you add the two A's, you add mod 4. When you add the two B's, you add mod 7. That's exactly the definition we just gave for how to do our overall group operation here. I'm just asking you to do it for as many groups as we have. This only asks you to do it for 2. But we know, we showed, you should have showed, that this is a group. Which means what? Which means it's closed. If I take 2 ordered n tuples like this, and I do this component-wise multiplication, A1, B1 is still an element of group 1. A2, B2 is still an element of group 2, and so on. So this stays closed. The operation is associative because each individual operation was associative, because it says up there G1 through Gn are all groups. And that means if I had A and B and C, it wouldn't matter if I did AB first and then C, or BC first and then A. It works both ways. Is there an identity in these things? Well, sure, you use the identity from group 1 in the first spot, the identity for group 2 in the second spot, the identity for group n in the nth spot. You just have to use it however many times. In our exam question, that meant that it wasn't just the number 0, it was the ordered pair 0, 0. Is there an inverse? Sure, because whatever this element is in group 1, it's got an inverse in group 1. Whatever element this is in group 2, it's got an inverse in group 2, and so on. So as long as each individual thing has an inverse, then this whole ordered thing has an inverse. This is a group. And we're going to call the resulting group the direct product of the groups that make it up. So in our exam, we had the direct product of Z4 and Z7. Questions? It turns out that if I am really just dealing with abelian groups every time, we prefer to use addition instead of multiplication for abelian groups. If all of these G's are abelian, then I want to use addition notation, in which case I'll write this as a sum. So instead of using an addition notation, a multiplication notation, we use this addition notation. That's not as common because the operation looks weird, that circled plus symbol. I see this notation in lots of other places, but I'm going to stick with times even when my groups are abelian, because I still think of this as a direct product, and that happens more generally. So as much as I like direct sum, I'm not going to use it very much. Questions? So far, it's all terminology. Pretty straightforward, yes? Let's suppose each group is finite. If each group is finite, GI has Ri things in it, then how many ordered sets can we get? Ordered n-tuples. If each group is finite, GI has RI things in it, then how many elements can I have in the set of ordered whatevers and tuples? How many things are in the direct product? Let's think of our example from the exam. We had Z4 cross Z7. How many things live in G?
Every pair with A being like 0, 1, 2, and 3, and then with B being 0 through 6.
Yes.
Any combination of those two numbers.
That's absolutely true. How many is that?
A lot.
It's actually much smaller than you think. How would you write out that set of ordered pairs? Physically, if I asked you to write them all down right now.
0, 0, 1, 0, 2, 0, 3, and then
I'd just make a grid, wouldn't I? All the ones that had 0 in the first spot, all the ones that had 1 in the first spot, 2 in the first spot, 3 in the first spot.
So it'd be
4 rows by,
7.
28.
you're done. That's for this group. Generalize. Group 1 has R1 things in it, 4. Group 2 has R2 things in it, 7, in general. G has R1, R2 things. R1, R2, R3, R4, all the way up to Rn. How many things are available? Multiply them all together. Let me, elements. I mean, Z2 by Z3. That's a small one. How many things? Presto. Let's work with this group for a minute. Write all 6 things out. What are my 6 things?
0, 0, 0, 1, 0, 2, and then 1, 0, and then 1, 1, 2.
Poof, presto. I have a group with 6 things in it. I've seen groups with 6 things before, haven't I? We made Cayley diagraphs of groups with 6 things before. Question. What group did we do that for? You wrote notes. You made pictures. You were all here. I did not hallucinate you into being.
The generating set in Z6 of 2 and 3.
We did it with the generating set of 2, 3. We also did it with a generating set of just 1, didn't we?
Yeah.
But it was still Z6, right?
Mm-hmm.
Z6 was cyclic. When we used the generator 1, we got all of them. When we used 2 and 3, we got the triangle inside the triangle. We couldn't quite see automatically whether it was cyclic. But that group of order 6 was cyclic. Here's a group of order 6. Is it cyclic? Yes, sir.
If we, if we showed that it was isomorphic to the other group, would that prove that it was also cyclic as well?
Yes, but in order to prove that it's isomorphic, you're going to have to find a one-to-one and onto connection that preserves your addition behavior, right?
Right.
I think it's actually easier if you show if this is cyclic, then you can say, oh, well then, I know what the generators are in Z6, right? I know the generator with 1 or I can generate with 5. Let's tie the generators together and then we can build the rest of it.
That was my gut too. I was just wondering in case that was the easier way.
Oh, that is absolutely the easier way, is to prove that this is cyclic. Then it must be Z6. How do I show this is cyclic?
Could it be like component-wise adding one to each, like, part of the ordered pair? So like if we look at just the first element, if we add one, we just go from the cycle from 0 to 1 back to 0. But if you go in the second element in the pair, you go 0, 1, 2, 0, 1, 2.
But 0 and 1 are not part of this group. Every element of this group is an ordered pair. So if you're going to work with elements of this group, you need to work with an ordered pair. That's the hard part. But I think you're onto something.
We do it with 1, 0, and 0, 1.
I could. Let's see. But that wouldn't prove it was cyclic. That would just prove it has a finite generating set. In order to be cyclic, I have to have a generating set of size 1.
Would you do this 1, 1?
Let's try. Now remember, my operation is addition, but in the first component, it's addition mod 2, and in the second component, it's addition mod 3. So when I add, I have to add carefully.
So you get 0, 2.
Great. So if I add 1, 1 again,
1, 0.
I'm adding mod 3 in the second component. 1, 0 plus 1, 1.
0, 1.
0, 1 plus 1, 1. 1, 2 plus 1, 1.
0, 0.
Which means if I add 1, 1 again, I get back to 1, 1, right? So from 1, 1, I got them all. Start with 1, 1 itself. 1, 2, 3, 4, 5, 6. I got them all. This group is cyclic. We found a generator. Ian, now I can make the isomorphism. Z2 cross Z3 is isomorphic to Z6 if I align these two elements. When I add this to itself, I get 0, 2. When I add this to itself, I get 2. When I add this to 1, 1, Notice the identity mapped to the identity. Didn't we say that had to be true for every homomorphism? And the generator went to the generator. This map is not just a homomorphism, it's one-to-one and onto this map. That's a really crappy looking phi. This map is an isomorphism. Hot damn. Now you're not wrong. I could have done 1, 0, and 0, 1. And that would have shown me a generating set of 3, 4, right? Which would have given me one of those triangles, the 1, 3, 5 triangle, and it would have given me the 0, 2, 4 triangle, and it would have given it to me backwards. I would have had a generating set, but it wouldn't have shown me it was cyclic. To be cyclic, you need a single generator. Questions? I picture Z2 cross Z3 as two dials. One dial only contains the numbers 0, 1. One dial contains the numbers 0, 1, and 2. And you can only turn them one click each time, right? Both of them have to turn at the same rate. 1, 1, 1, 1, 1, 1. And you get 6 different possible readouts on both dials. And there they are in the order they appear. I found a generator. Let's try it again. This group only has, oh good. Smaller, it should be easier. Write them all out and tell me whether or not it's cyclic. It is? What's your generator?
Same as the last one, 0, 1.
Well, the last one was 1, 1.
1, 1, sorry.
So let's use 1, 1. 1, 1 plus 1, 1 is,
0, 0.
wait a minute. If I add 1, 1 again, I get back to 1, 1.
Oh, I messed up then.
I'm only going to get 2 things out of this. The subgroup generated by 1, 1 only contains 2 things. 1, 1 and 0, 0. That's not going to work. Try something else.
It wouldn't be cyclic because you have to use 0, 1, and 1, 0.
And if I use 0, 1, then I'm never going to get anything in the first component.
If you use 1, 0, you won't get another one.
And if I use 0, 0, I never get anything other than 0, 0, right? I can never get all four of them. I am having the most substantial sense of deja vu in the universe. I've seen this before. Joke never gets old. Wait a minute, I've got a group of four things. It's not cyclic.
That means isomorphic Klein 4.
There are only two groups of order 4, Z4 and Klein 4. This is the Klein 4 group. As a matter of fact, you could let A be 1, 0, B be 0, 1, and then C would be 1, 1. Pretty sure it works no matter which way you assign those three elements. So this was not cyclic. The other one was. What's the difference?
The difference between the two is the first one had different like outputs. This one has the same output every time.
2, 2, 2, 3. So I have the chance to alternate things, right? What if I did 2, 4 or 3, 3? Page 88, I'm sorry, page 89 in the textbook does Z3 by Z3. So if they're doing 2 and 2, they do 3 and 3. And that's not cyclic either. Why?
It doesn't offset.
Doesn't offset. So if I did 2 and 4, why wouldn't that offset?
Because they're both even.
And 2 and 3 were,
Uneven.
oh, okay, what if I did 3 and 9?
Is it because 2 and 3 are relatively prime?
Bing! There's the magic word. It's not just that they're both even, that they have a common factor. Zm cross Zn, Zm times Zn, the direct product, is cyclic and isomorphic to Zmn if and only if those are relatively prime. By the way, this extends to more than 2. That is a cyclic group. A cyclic group of order 30. Which means I can do this with as many possible Zi's as you want, as long as they are pairwise relatively prime. But if I did Z2, Z3, Z4, no. 2 and 4 aren't relatively prime. Now that means that I can actually go the other way. Thinking of this just as the numbers 0 through 71, and clicking one at a time, that makes sense, right? Giant circle with 72 numbers on it. But I could also say it's two circles. One with 8 and one with 9. And those are isomorphic. As a matter of fact, as long as I know the prime factorization of this number, I can write the product of groups. Eight is 2 cubed, 9 is 3 squared. So there's the pi and the ri in each case. So here's a different way to think of Z72 as the ordered pairs 0 to 7 in the first coordinate, 0 to 8 in the second coordinate, or a dial of 8 and a dial of 9, clicking them through one at a time, will give me all 72 options because they don't line up. They don't synchronize at any point in time. Questions? Z72 is cyclic. But that means it's got a lot of subgroups, right? I could take the element 2 and look at what was generated by that. I could take the element 3 and look at what was generated by that. I could take the element 4 and look at what was generated by that. If I'm in Z8 by Z9, my elements are ordered pairs. How do I find the order of an element? By the way, I just pulled this out of thin air. I have no idea what the answer is to this. If I was in Z72, how would I do it? If I asked you to find the order of the subgroup generated by 4 in Z72, you should know how to answer that question. That was on the first exam.
Just 72 and 4.
Because we look at the subgroup generated by 4, right? The greatest common divisor of 4 and 72 is 4. So I look at 72 divided by 4, and that's how many elements there are. 72 over 4. 18? Now, in the exam, you were then asked to list them. I'm not making you do that here. But I think I can apply that in the same direction. I need, again, another piece from discrete number theory, least common multiple. So let's suppose I have a bunch of positive integers. Then the least common multiple of all of those integers is the generator of a cyclic group of all multiples of all of the Ri. Or in other words, the group of numbers so that Ri divides every one of those numbers for all I. So there was a method we used for finding least common multiples back in discrete. Method we used for finding greatest common divisors. That wasn't the Euclidean algorithm. Anybody remember? Hint, it had to do with primes.
The prime factorization is better than whatever they have in common and multiply together.
That gives me the greatest common factor. How do I get the least common multiple?
Multiply the ones that aren't in between.
Almost. I multiply everything. In the greatest common divisor, I use the lower power of each prime. In the least common multiple, I use the higher power of each prime. So here are three numbers. 3, 12, and 15. Let's find the least common multiple of those. Well, 3, that's just 3 to the 1. 12 is prime factorization. 15 is 3 times 5. Now I'm going to write them all with all of the primes. So this is 2 to the 0, 3 to the first, 5 to the 0. And this one is 2 squared, 3 to the first, 5 to the 0. And this is 2 to the 0, 3 to the 1, 5 to the 1. The greatest common divisor uses the lowest power of each. And in this case, that means the greatest common divisor is 3. The least common multiple uses the highest power of each prime. So the least common multiple is 2 squared, 3 to the first, 5 to the first, which is 4 times 15, which is 60. With me so far? Please remember the question I started with. What's the order of 2, 3 in Z8, Z9? Is this supposed to help me with this? So let's suppose I have an ordered n tuple in my direct product. 2, 3 in Z8, Z9. And I know the order of each one element in its respective group. Then the order of the element in the direct product is the least common multiple of the orders of each individual piece. How well do the dials sync up? I want to know the order of 2, 3 in Z8, Z9. I did tell you I did not know what the answer was. So let's figure it out right here, right now. In Z8, what's the order of 2? Four. You take the greatest common divisor, you divide the order of Z8 by it. The greatest common divisor of 2 and 8 is 2. 8 over 2 is 4. This is R1. The order of A1 in group 1, that's R1. In the second group, find the order of this element. Three. Again, my greatest common divisor. Take the order of the group, divide it by that greatest common divisor. That's R2. What is the least common multiple? 3 and 4. That was easy. So the order of 2, 3, the size of the subgroup generated by 2, 3 will be 12. The least common multiple of 3 and 4. I haven't listed them. I could if you really want to. I don't. But if I start with 2, 3, and I keep going, that's how many things I should get. The result may not be a cyclic group. 2, 3 may not give me a cyclic thing, but it will give me 12 things total if I look at what I can add. Now again, Z12 by Z60 by Z24 itself is not a cyclic group. And that has a huge number of things in it. But it's not cyclic because all of those are even. The greatest common divisor is not 1. Okay. What's the order of 8, 4, 10? I just have to do the same thing 3 times. I have to find the order of 8 in Z12. I have to find the order of 4 in Z60. I have to find the order of 10 in Z24. Was vergessen Sie? What do you get? One of the real phrases I know in German. That isn't rude. What are my 3 orders? No.
I was gonna say, need 60.
Aha! Because the order here, greatest common divisor of 8 and 12 is 4. 12 over 4 is 3. The greatest common divisor of 4 and 60 is 4. 60 over 4 is 15. The greatest common divisor of 10 and 24 is 2. 24 over 2 is 12. And the least common multiple, 350. We did this. Is 60. I don't know what they are. I don't know what the elements generated by that triple are going to be, but if I start generating, I should finish out at exactly 60 things. Questions?
Did you say it wouldn't be cyclic because it wouldn't represent like the entire group, or because the generating set itself won't get back to where it started?
The generating set has to get back to where it started, but I don't know if it will do so in a cyclic fashion.
Okay.
So I know that original group, Z12, Z60, Z24, that group is not cyclic because the greatest common divisor is 1. They're not relatively prime. So that means if I took 1, 1, 1, I couldn't get around the whole group. I need a larger generating set. Maybe I could use 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that would be a generating set of size 3, which means it wouldn't be cyclic, but it would be finitely generatable, right?
Yeah.
And that's a lot of cases, that's good enough, having a finite set of generators. But I would like to find the smallest generating set I can. And if my group is cyclic, then I know there should be a 1 that does it. I just don't know what that 1 is. But now that I know this one isn't cyclic, I know not to bother to try to find 1 generator. I'm going to need several generators. But that turns out to be true in general. I can find a generating set for any direct product of ZNs. At the very worst, I use 1, 0, 0, 0, 1, 0, 0, 0, 1 for however many things I've got, right? Our standard basis, linear algebra terms again. I can do it that way. But if I can find a smaller generating set, I'd like to. But I know in this case, I won't necessarily be able to find a generating set any smaller than size 3 because of the fact that these are all not relatively prime to each other. Better? All right. It turns out that this idea actually works for every finitely generated abelian group. I don't care what abelian group you are looking at. If your abelian group is finitely generated, it actually looks like one of these products. The real question is which one? Now, the PIs are primes. The RIs are natural numbers. And there could be multiple copies of Z at the end, because I said this was a finitely generated group, not a finite group. And the integers are finitely generated, despite it being infinite. This is unique up to a rearrangement of the factors. So Z8 by Z9 is the same thing as Z9 by Z8. I just switched the first coordinate with the second coordinate. Reflection through the x1, x2 axis. By the way, the number of copies of the integers that we have here at the end is an important number and was first studied by a guy by the name of Betti. So we call that the Betti number of the group. The number of copies of Z in this factorization is called the Betti number of G. If my group is finite, then the Betti number is 0. Like Z8 by Z9, 72 elements, we have a Betti number of 0. Z12 by Z60 by, oh God, that was ugly, right? Would have a lot of possibilities. But notice, this allows me to clearly show why the Klein 4 group and Z4 are different. Consider a group that is abelian of order 4. What's the prime factorization of 4? No, that's not a rhetorical question. And yes, you should be able to do that one fairly quickly. So that means I can either write Z4 or Z2 by Z2. 2 squared, or 2 to the first, 2 to the first. If I know the prime factorization of the size of my group, I know the possible different versions of my group. Somebody pick another number. Well, that's the one I just did. Another number, 6. Well, then there's only one option, right? If my group is of order 6, 6 is 2 times 3. So the only possible way to do this is like this. And that turns out to be isomorphic to Z6. But we know those are not isomorphic. They're only isomorphic when it's relatively prime. Let me go with something more highly composite. How about 24? What happens if I do a group of order 24? I need the prime factorization of 24.
2 cubed times 3.
Aha. So the first option is to split it up just like that. Z8 by Z3. And that would be isomorphic to Z24 because 8 and 3 are relatively prime. But I could subdivide that Z8, couldn't I? And I could do that in 2 more ways. I could either do it as a 2 and a 4, or I could do it as 3 2s. So here's an interesting idea. If you give me an abelian group with 24 things in it, there are only 3 ways to arrange those. A cyclic group, a 3-dimensional group, a group with triples in it, or a group with quadruples. Every abelian group of size 24 looks like one of those. Those are my only options. As the order of my group gets larger, the number of options gets bigger and bigger and bigger. But it comes down to the number of ways I can break up the prime factorization. What is the prime factorization of 360?
Is it 3 cubed times 2 squared times 5?
Yes. It's 36 times 10. So there's a 2 and a 5, and then that's 6 and 6, so there's 2 3s and 2 2s. So that gives me 3 2s, 2 3s, and a 5. So I'm going to get a Z5 in every one of my decompositions, right? And then I have to decide, do I keep the 2 3s together and make it a 9? Or do I split them apart? Do I keep the 3 2s together, make it an 8? Do I split them apart to be a 4 and a 2? Or do I split them apart to be 3 2s? So there are 3 options here. There are 2 options here. And then there's 1 option here. And now you get to play mix and match. One from column A, one from column B, one from column C. Which gives you how many options? And only 6. Which means if you give me a group with 360 things in it, it looks like one of these 6 options and nothing else. As long as it's abelian. There is another version of this. I call this the primary factor version. There's another version called the invariant factor version. So now my subscripts are different. They're D1 through DK, where DI is always bigger than or equal to 2, and DI divides evenly into DI plus 1. What the? Let's consider for a moment one of the options from up there. Let's look at Z2 by Z2 by Z2 by Z3 by Z3 by Z5. So I've taken the bottom option on each of these. I want to rearrange these. So here's what I do. I say to myself, I have 3 2s. I have 2 3s. I have a 5. Everywhere you see a blank, put a 1. Now multiply down. Notice the rightmost number divides the next one. This number divides this one. I can keep going from right to left. So that means I would write this as Z2 by Z6 by Z30. And these, each one divides the next one. Now Z6, that's a 2 and a 3. Those are relatively prime. So technically, that's Z2 times Z3, isn't it? And 2, 3, 5, those are all relatively prime. So those break up. So this is the same as that. I can turn my primary factor into an invariant factor with this little table idea. If I had a 4, if instead of 2, 2, 2, I'd written 2 times 4, then I would write a 4, then a 2, then a 1. Because it's 2 to the highest power. If I had the 9, I would write 9, 3, 1. I have to break this table up. There's an example in the text. Each different primary factor version has its own invariant version. I really don't give a rolling donut about whether or not you use the invariant version or the primary version. But I was doing some reading after I got the new edition of the textbook 2 years ago, and I was looking at invariant factors, and they show up more often than I thought they did. But I'm not an algebraist, and a lot of algebraists do use invariant factor versions as opposed to primary factor versions. Where does this mostly get used? It mostly gets used in computer control for degrees of freedom of articulated movement objects, which scared the bejeebers out of me because I didn't know that was the way you programmed those things. Okay. I did use a new word. I said that our group was decomposed. So let me expand on that. Our definition, G is decomposable if G is isomorphic to a direct product of two or more proper subgroups otherwise a group is indecomposable. This sounds like, hey, you can factor this group, right? And that's what we call them, invariant factors or primary factors. If your group can be factored, then it's a direct product of things in it. G is finite and indecomposable if and only if G is cyclic and the order of G is a prime power. So Z4 is indecomposable. But Z2 by Z2, because they're not isomorphic, is the decomposition for a different thing. By the way, this gives rise to subgroups. If I have a number M that divides the order of my group, then there exists a subgroup of that order. I was very particular about using 9 and 4 because they contain squares. And I was able to show, hey, this has an indecomposable part in it. If M is square free, pardon me, that's my note that I have a meeting, then any abelian group of order M is cyclic. So it turns out that squares and larger powers are what prevent me from being cyclic. I got to explore what happens with all of these factors. And this idea, we're going to come back to that one. I will see you all when? Next Thursday. You take a break. Have a wonderful rest of your day. If you came in late, I still have your homework.